Okay, let's pick up where we left off on Chapter 2 review. We've got it wants to find the equation of the normal line at x equals 1 of this function, the square root of x plus 3. So recall that what we're going to do is y minus the function value at 1 is equal to the opposite reciprocal of the derivative at 1 in this case, all times x minus 1. So we have y minus y1 equals m times x minus x1. And remember, it's the opposite reciprocal for the normal line, or the perpendicular line. So let's go ahead and find what f of 1 is equal to. It would be the square root of 1 plus 3, which equals 4. So we have y minus 4, and we'll just leave this part blank right here. No, we need to fill that out, and we have x minus 1. So we'll come back to this in a bit. So now we have a couple things we can do. We can either find the derivative at 1, which would be equal to the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. Or we have a choice to find the derivative in terms of x in general, and that would equal the limit as h approaches 0 of f of x plus h minus f of x. And either way we'll get the right answer. If we use the second method, method 2 here, then we have to find the answer in terms of x and then plug in 1 to find the derivative of that slope of the tangent line. So I think we'll use method 2. So let's try that over here. Limit as h approaches 0 of square root of x plus h plus 3 minus square root of x plus 3 all over h. And let's see if we could simplify. Well, we notice that we have this negative being distributed, and we have a 3 minus 3 then, so that cancels out, which is very helpful. So we have x plus h minus the square root of x all over h, and it's the limit as h gets closer to 0. And of course this is the derivative, not at a specific point, but just the derivative of x. So you might recognize this, hopefully you recognize that this can be rationalized by multiplying by square root of x plus h plus the square root of x over itself. And we're not going to bother to distribute that h on the bottom. And of course we've done this a number of times now, so hopefully this should be a piece of cake. When you multiply those two together, you get x plus h. And remember, the outside and the inside terms, one's positive, one's negative, so they're going to cancel out. And so you just have what on the bottom? Or excuse me, the last term times the last term would be minus x over our h times that quantity x plus h that we use to rationalize this denominator, or this numerator. And of course it's still the limit as h is approaching 0. Okay, well, hopefully we can see right away that we can simplify that, and looks like the h is canceled, and we have what do we have? Oh, we have h over h times the quantity x plus h plus the square root of x. And if we plug this in, we get, well, first we have to simplify it, and we get 1 over square root of x plus h plus the square root of x. And I'm thinking I maybe didn't distribute a negative properly because it's not what I should get. So anyway, we have 1 over the square root of x plus 0 plus the other square root of x to give us a quantity of 1 over 2 square root of x. No, that's proper. That's the correct answer. So that's our derivative in terms of x. And now we're going to simply plug in our x equals 1 to our derivative. So we have dy dx. And we're going to evaluate it at x equals 1. This is something I didn't bring up earlier, but it's good to start looking at this notation. When you put that little bar beside that, that says this is the value of the derivative when you evaluate it at x equals 1. So it's just a new notation for you to look at. So we have 1 over 2 square root of 1. So it's equal to 1/2. So the derivative of this function when x equals 1 is equal to 1/2. So you just simply plug in the opposite reciprocal of -2 up here, and that's good. You're good to go. Okay, let's take a look at number 9. Use the formal definition of the derivative to find the slope of the normal line to the curve. Definitely not going to set up that equation for you, but I will set up the limit as h approaches 0 to make sure you get on the right track. 1 over, so inside that parentheses we're going to put the x plus h, and then we're going to subtract this quantity 1 over x plus 1, and it's all over h. So we could multiply by the reciprocal of this. We can't plug in a 0 right now, obviously, or we could find a common denominator between these two, and that would help us to evaluate this. So I believe we'll multiply by the common denominator, or find a common denominator, I should say. So in order for me to find the common denominator, I'm going to multiply this left fraction right here by x plus 1 over x plus 1. Try that again. And this right-hand fraction over here, I'm going to multiply it by the denominator of the first one, which is x plus h plus 1 and x plus h plus 1. And then let's see what we get. Well, we have 1 times x plus 1 for the numerator, and then we have minus, remember we have our minus sign right here that's going to distribute to everybody, so we have minus x minus h and plus 1, oh, excuse me, minus 1. And our new common denominator is x plus h plus 1 times x plus 1. Notice I was pretty careful about putting my parentheses here, indicate the two terms. And this is all over h, and once again it's still the limit as h approaches 0. And let's go ahead and cancel what we can on the top. We have, I have an extra minus sign here, don't I? It should be a minus. Make that red. Okay, so let's go ahead and cancel. We have x minus an x. We have 1 minus a 1. And now we have a negative h over x plus h plus 1 times x plus 1, and that's all over h. So recall that we could multiply this fraction by the reciprocal of the denominator, or if you recall, we worked out that that's just simply canceling out. So I have negative 1 over, now, excuse me, now I'm going to go ahead and plug in h for 0. So I have x plus 1, because that h turned to 0. So that parentheses is not doing anything anymore. And then we have x plus 1. So this becomes negative 1 over x plus 1 squared. Alright, so remember, we're not quite done yet. You still have to plug in that x equals negative 4. Alright. Let's see, I wanted to reemphasize something that I mentioned in class, that the position function is sometimes written s of t, and the velocity function sometimes is written v of t, and acceleration is a of t. And I did briefly mention this, and we're going to do a lot more practice with this, but when you take the derivative of position, it'll give you velocity, and then if you take the derivative of velocity, it'll give you acceleration. So anyway, since they gave us the position function here, they want to know, find the velocity, and they don't directly tell you what to do, so it's important that you understand this relationship. So we're going to basically, we're not looking at a specific time period, so we're just going to find dy over dx, but you notice that nothing here is given in terms of that, so it's going to be what? It's going to be over t, so it's going to be the derivative of s of t over dt. Alright, so don't get too hung up on this notation, but anyway, so let's take a look at it. It's the limit as h approaches 0 of what? We have our first function is going to be t plus h, so we have t plus h minus t squared. So into t we're going to replace it with t plus h, and then we're going to subtract the t minus t squared, and simplify now. So what's our, this parentheses here at first is not doing anything, so we'll just go ahead and rewrite t plus h. And now we're going to be very careful here when we take our shortcut. We have t squared plus 2th plus h squared. And now just recall that this subtraction has to be distributed to each one of these three elements in here. And then of course at the last part of our numerator we've got to distribute that. So we have a minus t and a plus t squared all over our h. So we still have our limit here. And let's go ahead and clean this up. We have t plus h minus a t squared minus a 2th minus h squared minus t plus t squared all over h. Okay, easy to make a mistake. Just slow down and take your time. So we have t minus t, that cancels. We have a negative t squared here, which cancels with this positive t squared. And that looks like about it, but everything else has an h term in it, so we're going to factor the highest power, which is only to the first power, which is what we wanted. Don't forget that when you factor that out, it's equal to 1 minus 2t minus h all over h. And we're going to be able to simplify, cancel those two h's out, And now we're going to go ahead and plug in 0 for h, and we have 1 minus 2t minus 0. So our derivative is 1 minus 2t, and this is the velocity of this function. So remember, it might also be expressed in terms of v of t. Alright, hopefully this was helpful. And let's see. We have a couple more we can do real quick. 11 and 12. Just be careful and label what you're given so that you don't make a mistake. The left picture is the function. So I'm going to go ahead and put f of x right here. And they want us to sketch the derivative f prime of x on the right graph. So what are we going to do here is, let's just notice a few things. One is, we'll use red for negative. We have a negative slope here, and it looks like it's pretty steep, and then it's still negative here, but it's starting to flatten out a little bit, right? In fact, somewhere around here, the slope is equal to 0, right around the origin. And so remember that the slope of these tangent lines that we just identified, big negative, still big negative, but getting smaller, the derivative is the slope of these tangent lines. So we're just going to come over here and we're going to put some negative values here. And we notice that at the origin it's equal to 0, right? And then it never turns positive, does it? It never turns positive. It just kind of gradually gets here. And then as soon as we make that corner where we have a slope equal to 0, it starts gradually getting more negative, and then a little bit more negative, and a lot more negative, and a lot more negative, and a lot more negative. So this thing isn't linear, I don't think. It looks like it's probably some sort of quadratic that I didn't draw very well. Anyway, upside down parabola. So it's probably looking like this. Okay. So hopefully that'll help you out a little bit. And on number 12, before we just jump right into it, let's label it. The left picture is the derivative. So they've given us the derivative, and they want us to come up with a possible function value. So just remember that there's more than one answer that's correct, but the shape is what has to be the same. Well, let's go and let's take a look at what this means. Here, our derivative is a negative 10 right here, and then somewhere here it looks like it's negative 5. At negative 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, yep. And then the derivative is equal to 0 right here. So we have a function that is negative, but it's approaching 0. So, and then once we pass the origin, it starts getting positive, more positive, more positive, and finally it reaches 10 when I'm at 10. So what is this thing doing? Let's draw a couple scenarios. Remember, when the slope equals 0, it's either going to be a relative max, or it could be a relative minimum, like this. Well, let's take a look at some of the characteristics here. Here, as we move from left to right, it's very positive, getting a little bit smaller, and a little bit smaller as we inch along. And then right here we have a horizontal tangent line, so the slope is equal to 0 right there in the middle. And then it becomes a little bit negative, more negative, more negative, more negative as we move on. So that's not what we're describing in problem 12. We're doing just the opposite, right? We have a very large negative slope, and the function is decreasing. And then the slope is still negative, but it's getting smaller whenever we hit our relative minimum. We have a horizontal tangent, so our slope is equal to 0 right there in the middle, and then as we turn the corner we get positive, more positive, more positive. So it looks like we've got a situation that could be described by this one. So let's go ahead and graph up a possible solution. Now, the reason I said it was possible, because it's possible that this graph could do this, right? And it's also possible that this same graph could be shifted up or down. So we really can't tell for sure, but all we do know is that this has to be a minimum here, and it has to be a relative minimum, and it's decreasing as we move from left to right, and then we start increasing again. So anyway, we will stop it now.